Good afternoon. My name is Andrea Watson, and I'm Tualatin Valley Water District's Public Information and Public Affairs Supervisor, and I'm going to kick us off today. I would like to point out a couple features. One of them is that the format of today's presentation is going to be a brief presentation, followed by a moderated question and answer period. If you are accessing this event online, you can type your questions into the chat. That looks like a little thought bubble with a question mark in it, and a little slide later on will show you what that looks like. And we're also a public agency, so this event will be recorded today, and it will be placed on the website and the YouTube channel for Tualatin Valley Water District after the event. So it's my pleasure today to introduce our host. And our host is Carrie Pack. She's a professional engineer. She serves as chief engineer here at Tualatin Valley Water District, and that's a position that she's held since February of 2016. Carrie is the district's first female chief engineer, and as the chief engineer, she leads and manages a team of water professionals who have the responsibility for the core mission, which is to deliver clean and great tasting water to your homes and businesses. She has been an engineer for over 30 years with experience in stormwater, wastewater, and water resources engineering. Her team comprises almost half of the staff that work at Tualatin Valley Water District. More importantly, Carrie's a mother of 4 wonderful children. In her free time, she enjoys traveling with her family, where she tortures them by stopping for pictures of manhole covers, valve covers, fire hydrants, and other interesting water infrastructure. And you can email her at carrie.pack, P-A-K, at tvwd.org, and she'll send you some of those pictures. So I'm going to hand it over to you, Carrie. Thank you for hosting today.
Thank you, Andrea, and thank you, everyone, for joining us today. This edition of Talking Water, the Anatomy and Physiology of Water Distribution System. Last month, we opened our lobby for customer payments. So we're seeing some of you some of our customers coming to the office for services, and we really love seeing your faces, and we miss seeing you. So it's, we're hoping that the COVID thing's going to be behind us sooner than later. So today's presentation will be given by Pete Boone. Pete is the TVWD's Water Operations Division Manager. Pete has been working at the Tualatin Valley Water District since 2008. Pete began his services as an engineer and has worked on a wide variety of infrastructure improvement projects over the years. In 2017, Pete transitioned to the Water Operations Division, where he leads our team of excellent water works operators who operate all aspects of TVWD's water system. He is a registered professional engineer and a professional land surveyor. Pete earned his degrees in forest engineering and civil engineering from Oregon State University. Pete when he's not working, he enjoys outdoor activities like hiking, hunting, fishing, and foraging. He and his wife, Selena, live in Forest Grove, where Pete is also a volunteer firefighter and an EMT for Forest Grove Fire and Rescue. So he's a little bit of a slacker, I think. Also joining us today is water quality expert Joel Carey, who manages the Water Resources Division Manager. Among other things, this division is responsible for all aspects of water quality monitoring. His division produces the annual water quality report, which summarizes the thousands of water samples that are taken regularly to assure water quality meets or exceeds all water quality requirements. So I have the honor of introducing both of these folks, and I'm completely convinced that you're going to be thrilled with presentation from Pete Boone this afternoon. Take it away, Pete.
All right, thanks, Carrie. And thank you all again for joining us. I love to talk about our water system. I love to talk about our operators, the folks that make this system work. And it's a really neat thing to do. And a lot of times I think the water industry, we're not necessarily out in front, and you don't always hear from us. So we love to have this opportunity to to talk about the system and how it works, and we're glad that you joined us. So here we go. So this is going to be the anatomy and physiology of your water distribution system. So I'll use my experience as an EMT and a little bit of emergency medicine to talk about the corollaries between our human bodies and how the water system operates. So again, type your questions in the chat as we go. I'll try to cover this material in only about 25-30 minutes, so give us plenty of time for some interaction when we're all done, because that's the best part of these is hearing from our customers and being able to answer your questions. So anatomy and physiology, what is that? So anatomy is the structure of things, the components that make up different parts of systems, and physiology is how they interact with each other and what kind of processes and functions that system does as it operates. So our human bodies are made up of all of our body parts, and then the physiology is how does it all work together. Water system is very similar. But before we get into that, I want to talk about chlorination and disinfection of drinking water. So prior to chlorination of drinking water, people getting water and drinking it was a big contributor to disease. And it wasn't until about the early 1900s that became common to use chlorine as a way to disinfect water and to keep those diseases from spreading. And once humans figured that out and started doing it, it had dramatic positive impacts on public health. So again, this came out of Europe in the late 1890s. It moved to the US shortly thereafter. And you can see on the graph there just that dramatic effect it had on public health. So disease outbreaks that were related to water dropped dramatically because of that. So it's a very important public health thing that we have chlorine in the drinking water, because it provides that barrier against pathogens. And it's a very small amount. So we're talking in the like 1 part per million range is what the amount of chlorine that's in the water, and it varies. So it can be below that, it can be a little bit above. So we're talking about a very small amount, but that's really all it takes to provide that barrier. Now, chlorine residual in the water does decline over time. And as it declines, and even when it's all gone, it doesn't necessarily mean your water's not safe to drink. It's just that barrier has degraded a little bit. So that'll be an important concept as we talk about some of this stuff today. And again, I can't overstate the importance of this as a public health measure and what it's done for our society. All right, back to anatomy and physiology here. So here we are in the region. This is Tualatin Valley Water District and where we lie in respect to some of the cities and other features of our region. So we have a couple different sources of water supply. We get water from the Joint Water Commission. That's the JWC that you see on the map. And that's a system that has raw water stored in Barney Reservoir, in Scoggins Reservoir, and has a treatment plant out by Forest Grove where I live. And there's some other partner agencies that get their water from the JWC. We're one of those, along with the city of Hillsborough and the city of Beaverton and the city of Forest Grove. We also get water from Portland. So the majority of our water supply actually comes in from Portland, from the Portland Water Bureau. That comes out of the Bull Run watershed. They also have the Columbia South Shore well field, and we pipe that down to our region. And we're also working on the Willamette water supply system. So this is going to be a new water supply system that pulls water out of the Willamette at Wilsonville, pipes that up to Sherwood, where we will construct a water treatment plant, and then on up to both Tualatin Valley Water District, and again, City Hillsborough and City Beaverton are also partners in that project. So pretty exciting to see that in construction now. And the Willamette has been successfully used as a drinking water supply for both the City of Wilsonville and the City of Sherwood now for, gosh, about 16 or 17 years. So proven source of water. We're going to be relying on that starting in 2026. Okay, now if we zoom into our service area, here we are again. So Tualatin Valley Water District, we cover about 45 square miles. If you look at the map there, we're a little more than 10 miles wide, a little more than 10 miles from north to south. And in that service area, we serve to about 230,000 people. So 250,000 residents of Washington County rely on us to deliver their drinking water. We do that through about 60,000 individual service connections, individual water meters. And most of those are residential. So a lot of folks live out here, but we also do serve industrial customers, a lot of commercial, and a wide variety of folks. So if we zoom in yet again and now start to look at topography, the blue line on our map there runs from Cooper Mountain to the south, which is about the southern boundary of our main service area, straight north, roughly along the alignment of 185th Avenue, if you're familiar with that. And then if we cross 26 and start to turn towards the east and head up into the West Hills, a profile of that blue line is what you see at the bottom of the screen. So what I'm talking about here is we serve a wide range of elevations. And elevation is what sets the pressure of the water in our system exactly the same as the pressure in a lake. So as you go deeper in the lake, the water pressure increases. As you go down the hill in a water system, the water pressure increases. So important concept to think about when you look at that range of elevation that we serve. Now, if our entire system was one pressure zone, at the bottom of that, and the valley floor across the Loa, different parts of our system that are kind of at the lower elevations, that pressure would be way too much. So it'd be about 260 pounds per square inch, which would just be unusable from a plumbing perspective. So if you opened your faucet with 260 pounds on it, you'd have water spraying everywhere. So the physiology aspect of that, if our own blood pressure in our bodies was exceedingly high, our doctors would be working with us to bring that down. So much the same way that we manage pressure in the water system. Too much is not a good thing. So what we do is we break that into different pressure zones, and we try to keep that service pressure, what's delivered to your homes. It still varies quite a bit, but we're shooting for more than 50 psi, and we try to keep that in a manageable range. If we get above 80 psi in our system, then the plumbing code requires that your home has an individual pressure regulator on it, so that the pressure in your own pipes doesn't exceed the 80 psi mark. So we break that up into the different elevation zones. Most of those are fed by at least one water reservoir, and sometimes we use pressure regulating valves to further refine that pressure. So that's how we keep that pressure in our own system in the right zone where we want to be. One of the benefits of both of our supplies coming in from both the east and the west is they arrive to us at an elevation, if you will, at a pressure that allows us to send that out to a lot of our customers just via gravity. So we don't have to pump and add more energy to that water. We can let that go out into our system, fill our reservoirs, and not have to be pumped and sent around using energy. So nice benefit that we glean there. But when we do have to get up into the higher elevations, we do pump that, and we'll talk about that here in a little more detail in a minute. So when you start thinking about where those pressure zones and the boundaries of those are across the system, here it is in the two-dimensional space. So on the south end of our map here, you see a cluster of pressure zones. That's the Cooper Mountain area. And then across the valley floor, we've got our 385 zone, our 435 zone, and those numbers correspond to the elevation that the water would rise to if it were unconfined. And then again, as we go north and east into the West Hills, we've got a couple other bands of pressure zones as we move across the system. And we also serve down to the south and east on the map there, our Metzger service area down near Tigard. Same thing, it's divided up into a couple different pressure zones. All right, so pumping, I talked about when we have to lift water and get it up to our higher elevation customers, We do that through, we have a variety of pump stations across the district, 13 in fact. Most of those stations have multiple pumps within them. We are all electric. We are driven by PGE power, but we also have backup power generators. If there is an outage, we can fire up our generators and continue to pump water. And of course, the corollary here with our own bodies and the anatomy piece would be our heart. So these are our cardiac units here in our pump stations, and that's how we lift water up and serve our higher elevations. Now, once it gets up there, we want to have some storage in our system, and we do that through a network of reservoirs. They are a variety of sizes, from 125,000 gallons all the way up to 10 million, and a total storage capacity, if everything was full at the same time, of about 67 million gallons. So quite a bit of water. And we'll talk about how we manage that storage and make sure that we keep it fresh, because bigger is not necessarily better when it comes to water tanks. So we want to right size those so that they'll meet our customer needs without having an excess of storage that can be hard to turn over and keep fresh. And when we think about that chlorine residual that we talked about earlier, as water ages and that chlorine residual declines, that's when we want to start using it up so that we maintain that level of chlorine in there as a barrier. So when you try to think about 67 million gallons, you know, how big is that in terms of volume, something we can all understand. So I did some rough math on the Moda Center. If that were full of water, it'd be about 200 million gallons. So we store 67 in our system and try to keep that turned over and nice and fresh for the water customers. Now, getting the water, you know, from those tanks out across the distribution system and to every home in our area requires a pretty significant network of pipes. So we got about 750 miles of water mains in a variety of sizes. So this ranges from 2-inch diameter all the way up to 54 inches. So pretty wide range there. And as you can imagine, you know, it's a network of pipes, a lot like our human body has a circulatory system, you know, going from large arteries all the way down to small capillaries, and serving all of our different organs. The majority of our pipes in the distribution system are 6 or 8 inch diameter. So most neighborhood streets have a 6 or an 8 inch pipe that's delivering water down the street, serving all the fire hydrants for fire protection, but then also to those individual service lines that go to the meters. Now, the size of those pipes, those typically the 6 or 8 inch, is dictated by the fire flow that we need to deliver. So when the fire department shows up and they need to flow a bunch of water, we need a large enough pipe that can deliver that. If we didn't have a fire protection aspect to our to what we do as a district, and all we had to serve was drinking water, we could do that through a smaller diameter pipe, because folks using water in their homes is a much lower demand on those pipes, and they wouldn't need to be as large. But obviously we provide fire protection, and we need to have that capacity available whenever it's needed. And of course, I talked about our human circulatory system and how that does much the same function in our human body of moving oxygenated blood around to all of our organs. Okay, so I'll take just a quick break and remind folks, maybe if you joined us after I'd already started, if you have questions, type them in the chat. There's a little chat bubble at the top of your screen where you can access that. And we'd love to hear your questions. Let us know what topics you'd like to hear more about, and we'll have a moment here to work through those questions when I get a little further along. So, all right, jumping back in, I'm going to talk about a computer system that we have. It's called Scada. That's an acronym for Supervisory Control and Data Acquisition. And this is really the brains of our water system and the central nervous system. What it does is it monitors and controls through a network of sensors that's all across the system. So it's measuring water pressure, water flow, depth of water in tanks, flow rate coming out of a pump station, all kinds of different things, even water quality parameters. So it can measure the amount of chlorine, the pH of the water that's out across the system where we have different chemical analyzers. And it brings all that back to a central brain and displays this information for our operators to see, but it also has quite a few layers of automation built into that so that it can make adjustments as needed without our operators having to intervene. So amazing system, very valuable to us. In the days prior to Scada, water operations involved a lot of driving around and taking measurements, taking samples, looking in hatches and things like that. So huge advantage to have this available to us. And of course, in our human bodies, much like our nerves and our brain and how that detects different things that we're into, touch and function and controls our movements. Very much the same thing. All right, so how does this relate? Now, if anyone's ever had to go to the hospital and be hooked up to a monitor, this is what doctors are using to see what's going on in our bodies. So they're measuring all the different functions: heart rate, blood pressure, oxygen saturation, and then using that information to make decisions about different interventions that they might have to do. So very similar to our Scada system. Now, this is a screen from Scada that's showing just those kinds of things going on in the system. So just this stack of lines is showing us the chlorine residual in the water. Looks like we're running from about a 0.6 to a 1 part per million in this particular location. We've got a pressure measurement. So this is showing a period of time, about 24 hours of data of what happened in this part of our system. We had some pumping, sending water out to customers. So we had a flow rate that was adjusting as customer needs were changing, and then a water level in a tank that was, again, fluctuating as things changed, and we were pumping water in, and customers were drawing that back out of that particular reservoir. Okay, so to summarize, we've got a couple different sources of supply. We bring water into our system and move it around. We store some. We have to pump it up to higher elevations, and then we divide our system into pressure zones to manage that pressure when it gets delivered to the homes. We do that through our network of pipes, and we monitor and control that through our Scada computer network. So quite the set of different components here to build our water system. And again, if you have questions, type them in the chat, and we can cover those topics as we wrap up here in a few minutes. All right, so let's switch gears. We talked about anatomy. Let's talk about the physiology of this water system and how it all works together. So our objectives here when we're talking about water system operation, number one, we want to manage supply to meet demand. So when we talk about demand, that's the volume of water that our customers are using over a certain period of time. So typically we think of that in a daily sense, so millions of gallons per day. And we'll talk about how that fluctuates throughout the year. We obviously want to deliver that at an adequate pressure. We talked about that. We don't want it to be too low. We don't want it to be too high. And so we're controlling that pressure that gets delivered. And really importantly, we want that water to be of high quality. It obviously needs to be safe for drinking. So we manage that chlorine residual, make sure that we have a barrier against pathogens there. We try to manage water age and make sure that we're using that water up and getting it out to our customers and replacing it with fresh water. And the aesthetics of that water, so the taste and the different components to it are of high quality. And obviously we want to minimize service disruptions. So I think we do a really good job of this. I think most folks hopefully on the call have had very reliable water service if there are customers of TVWD. And we take that very seriously, and so we want that to be, we want to be the utility that you don't have to think about, that we're always there, that the water always comes on when you turn on your tap. So we work very hard to achieve that. So daily demand and water age. like I said, this fluctuates throughout the year. So the period that we're kind of transitioning out of, if you think of the winter and spring, when folks are not irrigating and not using a lot of water outside, our daily demand, the amount of water that we send to our customers is about 16 million gallons per day, and that changes. It'll go down to 15, it'll go up to 18, but it's fairly steady in that range. In the summertime, when things heat up, when we have nice weather like we're having today, and especially later into June and July, folks start irrigating, they're washing cars, they're doing different things to use water more outside the home. Our demand will go up sometimes as high as 45 million gallons a day. So a pretty big change from that winter daily demand. That can be mostly driven by temperature, mostly driven by rain, because folks are irrigating, and if it rains quite a bit, they'll turn off their sprinklers, our demand comes down, and then vice versa. We talked about that water age. So if we're not sending out a lot of water to our customers, the age of that water, so the time that it has elapsed since we brought it into our system, can increase, and that will drive the chlorine residual down as it degrades over time. So we have to manage storage. We have to manage the amount of water that we're keeping in those tanks. Not only that volume, but change it, turn it over, cycle it up and down, and make sure that we're keeping everything turned over and maintaining that chlorine residual. So when we think about Scada again, and we look back at this particular tank, think about the concept of respiration, of breathing air in and out. We try to do the same thing with our reservoirs. So take in a nice big breath. That's going to be fresh water coming in from our supplies, and mix that up in the tank, and then slow down a little bit with the pumping rate. Let that go back out to feed our customers, and try to cycle those tanks up and down. Now, our own bodies do some pretty amazing things under exertion. So if we go out and exercise, our muscles are going to be using more oxygen out of our blood. Our bodies are going to compensate for that by increasing our pulse rate, increasing our respiration rate, and delivering more as our bodies demand it. And our water system does compensate and does react in very similar ways. So as our demand increases, a tank level might drop to meet that demand. So it's pulling water out and making sure that it's available for our customers. And likewise, if demand drops, and we're going to be still bringing water in, those tanks are going to fill back up. That's how we induce that respiration. A lot of these changes happen in Scada automatically, so they're programmed in. So we think of that as automation. Our bodies do that same thing. They can detect changes going on and detect different things that are needed and make adjustments accordingly. Also, we have the ability to intervene in those processes. So our operators they're receiving information through Scada and other means all the time, and then they can intervene and make changes as warranted. So that intervention piece, much like a doctor might see something on the monitor and have to intervene to improve our own health in our bodies. So I'll give you a couple examples of that. This is what a main break looks like on the street. So our system is bleeding. We've had a leak in a pipe. It's pressurized water in the pipes, and that's going to be coming out up to the surface. And this is something that we have to respond to and repair. So we're hemorrhaging. We're losing some water here, and our operators are going to be headed out there to take care of that. So what is the system doing while this is going on? And this is pretty cool. So back to Scada. So on the left side there, we see a graph over time. It's showing a water level in a tank. We've got a red line underneath that's the flow rate of the water that's coming into that tank from below. And on the profile, we can see this particular leak that we're going to showcase a little bit occurred in a part of our system on Cooper Mountain. So we pump out of a station that we call 189th because it's on 189th Avenue, and we pump that up to a tank that's named Goyak after a person who lived nearby. So we're pumping out of 189th. It's maintaining a reservoir level in the Goyak tank. And then all of a sudden, at 8 p.m. at night, this pipe broke. So here's what Scada did in response to that. The tank level started to drop. It's feeding that leak. It's trying to meet that demand and maintain pressure in the system. So it's going to naturally be dropping. The Scada system senses that, increases that pumping rate. So this compensation and is trying to meet that demand as well and keep that tank level from dropping too much. Now our operators got out there. They shut down that leak. They used the valves that we have throughout the system to isolate that, and they were able to stop that hemorrhaging. We got a tourniquet on that, and you can see when that happened because that's when the tank level starts to recover. Once that tank level recovered to a certain amount, Scada sensed that as well, was able to ramp down that pumping rate, and all was back to normal. So pretty cool example of automation and compensation. I'll show you another one. So this actually occurred not too far away from this first one and really impacted those same assets, the same tanks and pump stations. So this was just last weekend on Friday afternoon. There was a fire. So Tualatin Valley Fire and Rescue, one of our partners, goes to a house fire. And they connect to a hydrant, they start flowing water, and this same reaction occurs, right? So they've increased demand on our system, and they've induced a couple feet of drop in that tank as we delivered water to the hydrant. When they were done flowing water, they turned it off, and it just so happened that there was a weak spot in one of our pipes nearby, and that broke when those pressure changes were happening as water was flowing and then slowing down. So this gradient of demand continued on. Now it's just coming out of the street instead of being sprayed on the fire. So the fire department called us, said, hey, we got a problem out here. Our folks responded, went out, made an assessment of that, and started excavating to fix that problem. And this whole time, the water level is continuing to drop in that tank. And it dropped to a point where Scada had a setting to start another pump and said, okay, we've increased pumping rate a little bit. It wasn't quite enough. We're still dropping, so we're going to start a pump. And that's what you see here. But we had an issue in that pump station, and that pump tried to start and did not run very long and then tripped out. So we had a little bit of a fibrillation there, if you will, on the cardiac side. And the tank continued to drop. Well, it dropped to the point that it fired a third pump. It asked for another pump in the rotation. That one came on and was really the game changer in this event. So increased the pumping rate to about 2,000 gallons per minute. Allowed the operators to get their shutdown in place, stop that hemorrhage, and then really recovered to the point that it was no longer needed, and the first pump could then keep up, and away we go. So different levels of reaction and compensation are all automated into the system. There was not a person sitting at the screen turning knobs and pushing buttons to make all this happen. It's all programmed into our Scada. So pretty interesting piece of physiology and how the water system works. So I'll finish by thanking our operators. These folks work tirelessly to deliver water to your homes. Sometimes that work has to happen in the middle of the night. Sometimes it's on an emergency response basis, and really proud of these folks. They do an amazing job at delivering your water and making sure that it's safe to drink. So they really make things happen. Now it's your turn. So we hope you enjoyed that. We hope you got some good information out of this, and we'd love to hear your questions. So type those in the chat. Again, it's there. There's a little chat bubble, if you will, at the top of your screen, and let us know what things you want to hear more information about. Okay, thank you very much, Pete. This is a great presentation. We really enjoyed learning about the distribution system, and your analogy to anatomy and physiology just really seems to work well. So thank you for putting that together.
And we do have a host of subject matter experts. We try to anticipate your great questions. And we do find pretty much every month that you have excellent questions and you surprise us with a few. So we will be rounding out this subject matter experts and having a couple people jump in here to answer some questions who we haven't introduced already. But, you know, we have Pete and Carrie and Joel. They're our primary operation engineer, water quality, water resource team on the call today. But we're going to start. The first question is going to introduce a new expert here. We have Dave Kraska with us. And Dave is the Willamette Water Supply Program Director. So he really is in charge of the big construction project that's headed up there. And the first question is about that system. And one of our attendees wants to know, will Tigard and King City residents get their water from the new Willamette water supply? So Dave, if you could jump in here and answer that question, we'll let you kick off the Q&A.
Thanks, Andrea. Yeah, hi, this is Dave Kraska from, Andrea already introduced me, but in short, the answer is no. City of Tigard and as well as King City get their water supply from what was called the Lake Oswego Tigard project, and so that's a supply off the Clackamas River. We are, however, establishing an emergency connection with the City of Tigard. We have one in construction right now, and we are in discussions with Tigard and through Tigard also with King City about establishing a second emergency connection for that purpose. I need to note that I believe the City of Tigard has a part of their charter that does not allow Willamette water to supply drinking water to the city. So it would take a change to that charter for that to happen, and a lot of other intergovernmental agreements would have to be established in order for that to occur. But so we are establishing an emergency connection, but as it stands, there will not be a regular water supply from the Willamette River to Tigard or King City.
Okay, thanks, Dave. And I did also want to introduce one of my teammates. There's a couple of communicators here on the call that are helping with the technology and queuing up all of these activities that you know, that takes a little puppet mastery here behind the scenes. And so Justin Dyke, he's our outreach specialist. He does a lot of construction outreach. He's going to alternate the Q&A with me. And so the next question's his. Take it away, Justin.
Thanks, Andrea. This question I think will be a great one for Pete to answer. The question is, for a single home, do you supply a constant pressure, or what range of pressures should one house expect over time?
Yeah, good question. So the answer depends on where you are in the system. So some parts of our system are relatively constant, and other parts of our system have a little more fluctuation of pressure. But most times, even if you are in an area that has a fluctuation, it won't be more than probably 6 to 8 pounds, you know, from one day to the next, or even you know, summer to winter. So and that's those fluctuations will come from changes in water level in the reservoir, changes in demand in the system. You might notice low pressure, like for instance, the folks that lived you know, near the main breaks, near the fire that I talked about, they probably experienced some very low pressure during those events as the water is rushing through the system to meet those demands. So it's relatively constant, but it does change. And if you do experience low pressure or something that's really out of the ordinary for what you typically see, give us a call. Let us know. A lot of times our customers are the first ones to report issues because we don't have pressure sensors everywhere. So certainly let us know. 24 hours a day you can call and get a hold of our after hours duty folks if it's outside of normal business hours, and we can come take a look and see what's going on.
Great, thank you. It's, yep.
Yeah, I was just going to take the next question there, Andrew. I can see that. It looks like someone asked, how quickly on average do we turn over the entire 67 million gallons of stored water? Another good question. So first I should make clear, we rarely have 67 million gallons. So that would be if every tank was full to the brim, that would be that number. So Typically, it'll be in the 50 million gallon range, and in that spectrum of different reservoir sizes that we have. So this is a really difficult one to answer. It has a lot to do. Each reservoir is unique in how the water mixes inside that reservoir. So if we have a 5 million gallon tank, and on a particular day it's in a fill cycle, maybe it gets 200,000 gallons of fresh water into it. We would love for that water to mix completely and then be perfectly blended before it comes back out. But in reality, that doesn't always happen. So sometimes it's that 200,000 gallons that went in is the first water to come back out. And so we try to turn it over. We try to keep that water age low, but the water age in our system can be a couple weeks old if it's come in from our supplies and has to travel all the way across. So again, doesn't mean it's not safe to drink, doesn't mean that there's any problems with it, but yeah, it's traveled its way from either Bull Run or the treatment plant out by Forest Grove before it gets there.
And Pete, the next question might also be a good one for you and Joel Carey, our water resources manager. It is there any storage in the aquifers or just metal tanks?
Sure. So I can start with that. So it's both. We do store water in the basalt aquifer of Cooper Mountain. So we call that ASR. That's an acronym for Aquifer Storage and Recovery, and that's a system that includes a water well where we pump water into the ground during times when we have an abundance of water supply, typically in the winter months, and then we have the ability to pump that back out and send it to our customers. So that's an ASR system, and we do have one of those on Cooper Mountain. And then the rest of our storage is in tanks. So we have both metal and concrete tanks. We have tanks that sit on the ground. We have tanks that are buried underground. So a variety of storage reservoirs.
Thanks, Pete. The next question is both a compliment and a question. So, we like compliments, but they said they love your analogy on the human circulation system. And could you shed some light on what TVWD is doing to prevent cyber attacks on Scada? And I think Robert Witham, he's our emergency preparation coordinator. He'll take that at a high level. We don't have our IT staff with us today, and they're involved in that. But if you'll answer, Robert, that'd be great.
Yeah, sure. Yeah, I'll do my best here. We've had plenty of discussions about this and exercises around this. So our Scada system, to give a high level brief, is separated from any of our network operationally. It's a standalone system that works entirely by itself, and any type of data input from our operators and our Scada technicians is done through one point that's been identified as the only point that can get in and to make any kind of input, and that's it. There's no type of connection with, say, like the internet, so there's not really much of a risk of being able to get in there from the outside world and make any kind of changes. And also there's other multi-layers that if we have operators that are keeping an eye on it and watching things, and also physical systems that are in place that it's pretty limiting the type of ways they could possibly even change anything within the system. So that's probably about as high level as I can explain it.
Thanks, Robert. And I've got another question here. This would be probably a great one for Carrie Pack. Carrie, question is, do you do tours Once COVID is done, I have a group at Intel, software engineers, not water people, that would probably enjoy it.
Thank you for the question. So as you can tell from some of the response that Robert gave, a lot of our facilities there's some sensitivity in terms of security associated with where these facilities are and how we share them with our citizenries. Having said that, we've got a treatment plant that's coming online in 2026. We have reservoirs in places that if you knew where to find them, you could find them. We don't really want to advertise all of those things because of, some folks that might get to them that we really don't want to. But we would love to bring you out here to our headquarters site and show you some of the things that we're working on. And if there are areas where we're doing construction at the time, we'd be happy to take you out to those sites and show you what we do. We've got quite a few activities that we can share with anyone actually here at our headquarters site located in 1850 Southwest 170th Avenue in Beaverton. So drop us a line if you want to continue on with the tour of some sort. I think when we have the Willamette supply plant ready, that would be one of the best places to go to. And if you're interested in going to a plant right now, we can certainly schedule a tour out at the Joint Water Commission site that we are partnered with. And they do a really good tours out there as well. So give us a notice and let us know how we can help out.
Thank you, Carrie. And we do have a question here from Ben, and this is about earthquakes, and he wants to know, does the system have redundancy in case of an earthquake or another partial system failure? So I think Dave Kraska can talk about the Willamette water supply as being it's going to be the region's most seismically stable system. And then if Pete or Joel or any other subject matter experts want to add on to Dave's answer, that'd be great.
Thanks, Andrea. So the Willamette water supply system is in construction right now, and we're just wrapping up design. We've been in the design process the last few years, and as Andrea pointed out, it is the intent of that system is to be able to withstand ultimately a Cascadia subduction zone event. And so all of the design work that's taken place and all the construction activity that is to come is designed around that, so that when that event occurs, we will still be able to deliver water to the system. And so the benefit of doing that work now is that we could take advantage of all of the technological advances in the industry, all the things that have been learned since the last two big subduction zone events, the one in Indonesia in 2004 and then the Fukushima earthquake in 2011. A lot was learned from those events and is being employed on our system that we're designing right now. And so that will do a lot to improve seismic resiliency and water supply, not only to TVWD, but to our other project partners, the cities of Hillsborough and Beaverton, and as well to the region. We have emergency interconnections with others that we'll be able to support. So that gets the water to those systems, and then talk about seismic resiliency inside the TVWD network. Probably Pete Boone would be best to cover that topic.
Yeah, so we've made significant investments over the last 30 years in our water system from a seismic resiliency standpoint. So that's come in several different forms. So one is our storage reservoirs. So those are new reservoirs that are built in our system, are designed to a very high seismic standard, similar to what would be in California. We use a lot of pre-stressed concrete for those structures. We've made investments in pump stations and pipelines. So from that same perspective of trying to resist ground motion and not necessarily resist it in a rigid sense, but to be able to survive it. So So once we have water in our system, and if the big one happens, we'll be able to preserve that and maintain water service to hopefully most of our service area. We do expect a significant number of main breaks. If we get the Cascadia subduction zone earthquake, it will be a devastating event for the water system. We've got a whole list of improvements that we will be making over the next about 45 or 50 years to try to prepare for that. But yeah, so all the new infrastructure that's going in will be seismically resilient. But if you think about those 750 miles of pipelines, we can't replace them all. We just simply can't afford to do that. So we will be having response plans in place. We'll be having water distribution plans. If we can't deliver water to your home in the typical sense that we do through the system, we will have areas where folks can go and get water from us. So if that has to be at one of our reservoirs, we will be doing that. So we invest a lot in seismic resiliency, and we've made a lot of improvements, but we've got some more to do.
And I will just add that to Pete's comment about, we can't replace all of 752 miles of pipe, but we are in process of making some substantial investments in the major critical main lines. And those will be coming into our what we call capital improvement program, CIP plans in the years to come, probably after the Willamette supply program is completed. Having said that, we've done the emergency preparedness discussion through the Talking Water series in the past. We can't emphasize we can't emphasize strongly enough how you as a person should be ready for emergency backups. Should something happen, you need to have water at home for each person in your household and for your pets. And so we'd encourage you to explore our website, where Robert has done tremendously fabulous job of putting together emergency suggestions and kits for emergency situations. So, always be prepared. We're going to do our best job of making sure that water is available and deliverable to you. But in cases where it can't be, you need to be, relying on yourself as well. So I'll just add that to that discussion.
Thanks, Carrie. Always a great reminder of the importance of some emergency water at home. The next question is going to be for Joel Carey, Water Resources Manager. Joel, other than chlorine, are there any other chemicals added to water to make the water safe? Also, what filtration strategy do you recommend to customers?
Thanks, Justin. So the first part of that question, so the short answer is yes. There are things that are added to make the water safe. There's not a lot that we do, but the few basic things that we do currently right now to help with that would be pH adjustment, which is done by adding sodium hydroxide. So pH adjustment is something that we do to make sure the water is less corrosive. Part of what will be happening here in the coming years, including next year with some of our sources, will be adjusting what's called alkalinity of the water. So that process is done to make sure the water is also less corrosive. Those are probably the two main things that get added. One thing I should just note too, that one of our sources does include a type of chlorine species called chloramines, which is chlorine combined with a little bit of ammonia. That actually creates a longer lasting disinfectant. That's what Portland's used for quite some time. So it's something that our customers have received, and it's obviously, as Pete pointed out in his early presentation, there are limits, things we measure throughout that process to make sure it's safe. And last but not least, at least for TVWD, if you remember that map that we showed, the bigger section of TVWD is actually fluoridated right now at the entry points where our sources come in. The smaller section that is not, the smaller section we refer to as Metzger is not fluoridated. And in regarding the second question about filtration strategies recommended for customers, it really depends on what you're looking at. The most common thing we talk to our customers about are things like home filtration for lead, if you have copper plumbing with lead soldering, if you just simply want to remove the chlorine, at those levels. Those are a couple things. There's not really one best product per se for that. What we really try and provide our customers is at least the resources. So there's things to look for certification. So make sure the product you're buying says it does what you want it to do, and make sure it's certified from a third-party independent agency like UL, which is the little UL symbol, Water Quality Association, EPA approved. Any one of those types of stamps on it is what you want to look for to make sure that it's been independently verified. And short of that, if you have specific questions, shoot us an email, send it to waterquality@tvwd.org, and we will help connect you with resources and help you figure out what you might be looking at for your home.
Thank you, Joel. I really appreciate that. This next question is a little unclear to me who might be able to answer it, but I think somewhere between Pete and Carrie. If water demand increases, does the cost to manage this increase go up, or does overhead cost stay constant no matter what's used?
So I'll start with that question, and others can add to it. So it's a really good question. It's almost from an economics standpoint. So there's two parts to it. So there's kind of the micro level and then the macro level. So as water demand increases, so for instance, this summer when water demand goes up, yes, our costs do increase, but really only at the marginal level. So we're going to pump additional water, so we will pay a higher bill to PGE. We will have to, add a little bit more chemical to that just because the volume is going up. So incremental cost increases there, but our staffing stays the same. A lot of our fixed costs really don't change regardless of that amount of water that's being delivered. Now, at the macro level, over time, we do expect our water demand to increase, and so then we have to be prepared for that and build additional capacity into our system, into our supplies. So the Willamette system that Dave Kraska's team is working on, it's going to deliver an amount of water when it's built, but it's also going to be designed in a way that can, we can add capacity to that system over time as our customer demands do increase. So yeah, the costs do change, but on that near-term level, it's an incremental adjustment.
I think we can add economist to Pete's credentials after that answer. That's a great answer.
Pete's business card is going to run out of space here soon. The next question is going to be for another expert. A new one I'd like to introduce is Matt Oglesby. He's our asset manager, and he runs an array of programs that might help give some light into this question, I should say. The question is, how old are the pipes in the system, and what is the process of shifting to use a computer monitoring system? Did anything need to be physically changed?
So to kind of answer that first question, I'm going to go to our GIS system, which tracks all our assets in our system, and going to dive into the details of that by diving into our pipes range anywhere from that we know of from 80 years old to a couple weeks old. So, but on average, for the amount of pipe we have, it's about 30 years old, and the majority sit between about 50 to 20 years old. So we do get about the life out of our assets that we expect, at least for our pipes. And the other parts of that question, I guess I'm going to guess that it's dealing with our Scada system and the process of moving to monitoring our system that way. That happened quite a few years ago, and I don't know the process that what had to be physically changed. I know some stuff here at the district went completely from the computer, from old systems that we had that were paper-based, but I don't know. Maybe Pete has a better idea with the Scada system on that.
Yeah, so when Scada was implemented at the district, it was an evolution, and it continues to be an evolution. We're always adding to it and making improvements, but really it was adding sensors and gauges and meters and things like that. The pipes themselves and the pumps, they could operate without it. It's just Scada provides that layer of automation and the sensors that overlay on it. So not a lot of physical changes to be able to accommodate Scada.
Thanks, Pete. And the next question, and also I'd just like to note that we are up on time, but we won't leave the call. We'll stay on here and continue to field questions, so they'll be in the recording. If you have to leave, apologize for running over a little bit, but we've had over 26 questions, so we commit to staying here to answer as many of these as we can, because that's why we're here, is to serve you and to give you the information that you need. So Paul wants to know, will you treat the water from the Willamette for taste differences so it's comparable to the taste of the water received from Barney Reservoir? And Dave Kraska, again, our Willamette Water Supply Program Director, or Joel Carey will take this one, and we'll just keep working through the rest of the questions.
Thanks, Andrea. I'll give it a start, and then Joel can clean up after me. So at the Willamette Water Supply System, we're implementing technologies similar to what is being used at the existing Willamette River Water Treatment Plant down in Wilsonville. And those technologies are similar to what they use at the Joint Water Commission. And so the water from the Joint Water Commission and the water from the Willamette will be similar and somewhat different than what the supply has been from the Portland Water Bureau. I would say probably as far as the taste profile of the water from the Willamette, probably what will be noticeable is in the difference between is chlorine being used as the residual disinfectant, and that's what's used at the Joint Water Commission. So there would be a similarity in the taste of those two sources, and those two sources are different than as the Portland supply, which is chloraminated, as Pete pointed out. The one other thing that's going to perhaps make the taste profile slightly different than what you get from Barney, which comes from the Joint Water Commission, is that at the Willamette Water Supply System, we will be using ozone as a primary disinfectant, which is what they also use at the Willamette River Water Treatment Plant. And sometimes ozone can impart a bit of a flavor to the water that, if you're unfamiliar with it, you detect it. It's very faint. Some people have commented that it's kind of a fruity sort of flavor to it, but if you want to get a taste of what it's like, you can find out in Lake Oswego or Tigard or Wilsonville or Sherwood. All of those cities are currently using water that is ozonated and uses chlorine as the residual disinfectant. But sorry, long-winded question for your answer, but hopefully it gets to answering the question. It'll be similar, but somewhat different than what comes from Barney through the Joint Water Commission. So, Joel, what did I miss?
No, that was great, Dave. Nothing to clean up whatsoever. Just to add on to the end of it, I'll keep it short in the interest of time, but I think that's a really good point to bring up too, is that there are existing cities right now that are using the same type of treatment technologies out of the Willamette plant. Water treatment in the whole entire bucket that we talk about in this industry has a lot of similarities, so just keeping that in mind. But between like Lake Oswego Tigard plant and Wilsonville's plant, those customers that live in those agencies have always reported good, high quality tasting water. So, and just furthermore to add to this before I conclude is that we do have a project. It's the Water Supply Integration Project that is part of Dave's program, and a lot of us are part of the project team for that, looking at how we make sure that we implement this new source so that we minimize anything of that capacity. So, there are always little things that might change, but ideally what we're trying to work on is a really comprehensive plan that minimizes any of those disruptions so that our customers notice very little when this change occurs.
Thanks, Joel. The next question is going to be for Pete. With 67 million gallon max cap and using about 45 million gallons a day, how do you load balance the demand across the system? Is there a global SCADA dashboard to redirect water?
Yeah, great question. So really the way that our system functions is we just have to feed it. So if we bring in enough supply, the water will go where it's needed, right? So you saw some examples of how SCADA reacts and compensates. So if a particular part of our service area is using more water, SCADA is going to send it more water. As long as we bring in enough supply, those adjustments are automated, and the operators always have the opportunity to intervene and make adjustments if they need to. But really, it's as simple as bringing in enough to meet that demand. So our operators do turn the dials on our supplies. That's one of their major objectives, especially in the summertime when we're using more water. So, great question.
Yeah, the questions are always just so fantastic. So thank you everyone for that. And scrolling back up, lost my place here. Ralph wants to know what causes the bad taste in the drinking water from time to time. So I think maybe Joel, you might be the best to answer this.
Yeah, thank you, Andrea. It's a great question. I sincerely mean that, but it also is a question with a lot of potential answers. So, there's a whole host of things that could cause those changes. It could be a seasonal influence. The temperature water causes taste differences, which combined with home plumbing might be exacerbating some of your home plumbing issues if that's like a metallic taste to the water. Chlorinous compounds do cause taste and odor with water no matter what we do or say. Obviously, we add them for water safety, as Pete's slide points out, is one of the great advents of modern water treatment, and one of the reasons why, frankly, we have cities is the way we do is because of those modern advances. So, but taking that aside, you just can't escape the fact that chlorine does impart at times a taste and odor to it, most notably when it's actually on the reducing, when it's actually sort of what we'll call decaying. That actually can oftentimes create more of that. And again, there are things that like I mentioned, the source water, algal things that we do treat for in our treatment plants, but sometimes there are very minute things that could cause a slight taste to come through. Things that Dave mentioned as well. All that to say that there are a variety of things we often try and point out that taste doesn't necessarily associate with unsafe water, as it sounds like anyway. And again, my tried and true response in a lot of these forums, because it's so specific, if you do end up having something like that and it comes and goes periodically, shoot us an email, give us a call. Oftentimes, that's kind of how we can do the detective work to figure out what's going on. And the staff in Pete's group, operations, the staff in my group, the water quality team, our water quality experts and specialists, we get all kinds of interesting questions, and I can honestly tell you, we leave no stone unturned when we get that kind of stuff to help you figure it out. So let us know if something does occur. We will absolutely help, and specifics help as well.
And Joel, don't go too far away right now. The next one's also yours. In what place in the system does the water get purified?
Yeah, good question too. So like we've all been talking about, generally when you talk about that treatment process, it happens at the source, the treatment plant source itself. In these cases that we're talking about, our existing sources, Joint Water Commission, the water we purchased from Portland up at their headworks, and our future source, the Willamette River Water Treatment Plant, which takes, they take the raw water and do some degree of treatment within those treatment plants. There are oftentimes small things we would qualify as treatment that might happen in the system, and I say that with quotes, not anywhere near the same scale, but there are certain things we might do called booster chlorination, just to add a little bit of extra chlorine because of the size of the system and some of these other questions people have been asking about, water age, things that we want to monitor for and make sure that we're doing our best to optimize water quality. So, but in general terms, that real treatment, that purification process happens at those treatment plants. And then our team and the operations folks and everybody else involved does all this monitoring as it leaves there to make sure we're maintaining that quality.
Okay, excellent. I think this one might also be yours, Joel, or maybe Pete, but where is the Tigard water cleaned after it leaves the Bull Run Reservoir? The plant off of Durham and Tigard near the high school, or is that plant for sewage or what we would normally call wastewater treatment?
I think that might be sort of a couple questions in there. So yeah, I'll do my best, and if others just chime in or jump in on this one too. So yeah, so I guess we're talking about wastewater treatment too. So it's probably there are wastewater treatment plants in Durham that Clean Water Services operates. There's also the Rock Creek wastewater treatment plant. I assume that's what we're talking about, not drinking water treatment. If we are talking about drinking water treatment, City of Tigard and Lake Oswego have a partnership that plant actually comes out of the Clackamas, and it's located in West Lynn. And for Portland's sake, drinking water treatment for them happens up at Headworks, which is up the Sandy River at the sort of the start of the Bull Run watershed, if you will.
Thanks, Joel. The next one is going to be mainly for Pete, and Joel, you might want to stick around just to add in at the end. Question is, when there is a main break, how do you maintain cleanliness of the water? Is the chlorine residual sufficient at that point, or are there added measures that are used?
Yeah, so when pipes do break, one of the first things that happens, obviously, is water will be rushing out of that hole, and that pressure and the water pushing out is what keeps contaminants out of the pipe. So that actually helps us, and we're always very careful about the process that we go through to excavate, expose that hole before we throttle the water down and reduce that flow rate, because we want that clean water keeping everything out of the pipe. If we do have to do a shutdown, we will, like I said, excavate around the pipe, dewater around the pipe, so that when we turn off that flow of water, that things can't come back in. And if we have to cut out a bad section of pipe and replace it, we will actually chlorinate the pieces that we put back into the water system, make sure that they're disinfected before they go into service. And then as we restore pressure, we flush that off, and we take water quality samples and have those processed in the lab to make sure that there are no contaminants in the system. But that type of event is exactly why it's really important that we do maintain a chlorine residual in the water system, because that's when, it's when pressure is lost or different things can happen that contaminants have the possibility of entering. And if they do, we want to make sure that there's that barrier in place that the chlorine can take care of it. So, Joel, do you want to add that?
Yeah, all I'd add, which is great, Pete, exactly right, and all that stuff. And then the Water Resource Division includes a water quality team. So often what, as Pete just said, I think the key thing there was sort of the multi-barrier. It's like a multi-layered approach. You hear about in treatment, it's also kind of applied to distribution stuff as well. Staff that are out there fixing that will actually collect samples. Our staff collect samples throughout the system for surveillance. They'll do that routinely following some of these events, just as a matter of recourse, how we go throughout our system. So there's like a lot of layers of how we make sure that whole process is kept safe and we're not introducing something into the system.
Thanks, Joel. Thanks, Pete. Garrett has a question here. What are the greatest challenges and needs in our water distribution system? And where is there room for innovation? So I don't know, Pete, you want to take that?
I'll start it, and boy, there could be a lot of answers to this, and I think a lot of folks on the call could contribute, and I hope they do. I will say that probably one of the biggest challenges we face is our aging infrastructure. So you think about that 750 miles of pipeline that's buried in the ground, and most of it's made out of metal, and we all know how metal things do when they're outside in this environment or even buried in the ground. So they tend to corrode, they tend to degrade over time, and that causes us a lot of these pipe breaks. So, but not only that, but our pumps, our reservoirs to a certain extent, all of the infrastructure that we use to deliver your water is subject to aging and degradation over time. So making investments in that, keeping, managing those assets, doing the right amount of maintenance at the right times, scheduling those for replacement at the right times, and just meeting that challenge of aging infrastructure, I'd say is one of the things that we spend a lot of time on, and why we have so many smart folks working on these issues is making sure that we can afford to make those investments and still keep your water rates affordable. So there's a lot of chance for innovation. We try to keep tabs on the market, know what technology is available to us. We always try to, work smarter, not harder. Hate to use the cliche too much, but really there's a lot of opportunity, and I think we do a pretty good job of providing a reliable service and taking advantage of those opportunities when they arise.
Thanks, Pete. The next one's going to be for Joel Carey. Joel, any ideas or plans on how to handle potential for more frequent regional drought situations?
Yeah, another really great question. So I think one of the things it's probably a two-part question. So I think the first one is the kind of the bigger overarching picture that I want to paint for folks. This is very much the reason why the district, along with its partners for that matter, is moving to the WWSS. This provides us another high quality source for both short-term, long-term events, things like a short-term low precipitation event where we see flows go down or water availability starts to change, and then more long-term events that climate change might be impacting, where it's year to year. So having those multiple sources, for TBWD right now, we've always had multiple sources, and that strategy has always really played out well in terms of our ability to move those supplies around and understand that we can dial those back individually but still meet our demands as our customers need. So that really is one of the defining strategies of the district. The WWSS will replace Portland Water Bureau in 2026, and that source itself has had an extensive amount of analysis done in terms of our water rights availability, basin-wide availability for decades to come through a lot of other research. So it doesn't diminish the fact that that is a real thing. 2015 is a great example of what was very much one of the worst drought years in recent times, and we know from looking at the analysis that we would have still had plenty of availability from going to the Willamette when we are there in 2026 if we encounter those situations. Second part to that is there are also a lot of strategies that we look at in terms of our water management, our conservation efforts, water management in terms of making sure that we do our best to utilize every drop, that we are not wasting water in our system that leaks. We do water loss auditing all the time to make sure that we aren't wasting that precious resource. So there's a lot that goes on in that question, but absolutely we are looking at that stuff and taking a proactive approach by everything that we've explained today in our projects.
Thanks, Joel. And we are winding down the questions. I appreciate there's a number of you that are still hanging in here with us, and we will continue till we get through these. Is the water treated in each storage tank, or do you have a centralized treatment? Can you take that one, Joel?
Yes, I can take that one. Similar to the other question too. There's not treatment within those tanks. There's nothing that we've had to deploy at this point. Even aquifer storage and recovery, we push water in the ground that's already treated. So we do a lot of extensive monitoring to make sure that as it sits in the ground and that basalt aquifer underground, we don't see any negative impacts. Therefore, we don't have to do any additional treatment. The most we do is a little bit of supplemental, what's called booster chlorination, but that's definitely not the same as that type of big centralized treatment at our treatment plants that we do.
Thanks, Joel. Next one up is going to be for Pete. Is there a resource I can look at to see the water history of my property? I'm in the Metzger Triangle, have sump pumps, and found some old concrete drain pipes buried 3 to 4 feet deep in the middle of my backyard. Is there a way to find out where they go or what they were for? We have a fairy ring I'm hoping is not an old well.
Okay, so I think your best resource for this is if you're in the city of Tigard, their building department may have some historical databases that they could help you look through. If you're in the county, not within the city boundaries, then Clean Water Services may have some resources. We only deal with drinking water, so we don't deal with drainage and things like that. So probably not a lot of help that we can be there on this particular one. I will say, since you mentioned potentially having an old well, one, that's something to be careful with, because that could be, depending on how big it is, it could pose a hazard for folks falling into that, or animals. So make sure that if you do find that kind of thing on your property, that it is properly decommissioned. And if you have a well on your property in addition to water service from us, then we absolutely want to know about that and make sure that you have a proper backflow prevention device, so that we don't get any water moving back into our system from that well.
Thanks, Pete. This next question is: water pressure so high that when my kitchen faucets turned on or off, pipes under the house bang loudly. What is the danger of this? And I don't know who wants to tackle that one.
I can start on that one. So yeah, that can be a common occurrence. One, it's caused by it can be caused by pressure changes. It can be caused by high pressure. It can be as simple as there might be a pipe in your wall that's not secured, and so it's able to bounce and bang around. So I would suggest having your water pressure measured, and we can certainly come out and help with that. If you reach out to us, our customer service staff can help you measure what that pressure is. It may be that you have a pressure regulating valve in your plumbing. So if our water system pressure is higher than that 80 psi mark, the plumbing code does require that you have that pressure regulating valve. So those devices can change over time. They can fail, and so you may need to have a plumber come and help with that. But as far as the danger of that, it might be making noise and not be a danger at all. So it doesn't necessarily mean that there's going to be a problem, but it would be good to verify that pressure and see where it is.
Thanks, Pete. And the next question is going to be for Dave Kraska. Will you treat the water from the Willamette for taste differences so it is comparable to the taste of the water received from Barney Reservoir?
Yeah, this is Dave Kraska, and I think we addressed that question earlier, or was there additional information needed to address this question?
It might be a repeat, but it had looked like it came in a new question. Apologies if it is a repeat.
Okay, so just to recap, the water that we're getting from the Willamette will be similar to the water from Barney, which comes from the Joint Water Commission, in that both sources will have chlorine as opposed to chloramines as the residual disinfectant. But the water from the Willamette source might taste a little bit different because we're also using ozone as a treatment source. And if you're interested in what that water might taste like, if you're curious, I encourage you to go check out a restaurant or someplace like that where you might be able to get a glass of water in Lake Oswego, Tigard, Wilsonville, or Sherwood. All of those cities use water that will taste similar to the water that we'll get for the Willamette water supply system.
Okay, thanks, Dave. Again, we want to thank everyone for attending today. We are to the last question, and this one starts with a little bit of comment, but I'm just going to throw it out there because I don't know. I know a lot of you are involved in different nonprofit and organizations, so you might be able to help directly or refer this person to the right resources. But the Portland nonprofit Green Empowerment helps communities in some of the developing countries by providing clean water. Could we meet with you folks to assess how to define and implement a good enough, that's in quotes, water treatment system? And do you have an email that you can reach out to? So I would just encourage this person, if you will go back into the Q&A and give us your contact information, and then we'll let the subject matter experts handle this. But I think we can get you connected up with organizations that do this.
Yeah, Andrea, just to support, my response is going to be much like that. There's a lot of industry information from AWWA and Water Research Foundation, Association of Clean Water Agencies, that has resources for what are considered some of those practices in that type of situation. So happy to provide resources and create the links.
Okay, with that, I just again want to thank everyone for attending. We're going to close out this event today. And we will get a hold of you from the Green Empowerment nonprofit. If you could put your contact information, that would really help us out. But we did lose our host. She had our chief engineer. Want to do a shout out to Carrie Pack for being the host today, but she did have to leave for another meeting. So again, thank you, Joel. Thank you, Pete, for the presentation. Thank you for Dave and Robert and Matt and Justin and everyone behind the scenes. You know, we've got Frank Reed back here doing the switching. So want to thank everybody for making this event possible. And we look forward to joining you next month on May 19th, when we will be talking about efficient outdoor water use.
Thanks, everybody.
Thank you. Bye.